Hi. So let's do some bootstrapping. Okay. So we will use bootstrapping for calculating standard errors in the centered least absolute deviation estimator for that estimator. But this is a very general approach. So this is take this video can be used in for many other types of models. Okay. So the idea of bootstrapping is very general, and this is the topic for the next couple of slides. Okay, so basically you can say there's two ways of obtaining standard errors, or the distribution of a statistic. Either you can use that asymptotics, like for example theorem 12.3, that's establishing asymptotic normality for M estimators. There you know what the variance covariance matrix looks like. You can calculate it based on first and second order derivatives, and once you have your objective functions, just differentiating twice. Now we can't do that, right? Because this because this objective function that we have, if at least if we're not working with the smooth version of it, is non-differentiable. So we can't do that. Okay. I know Powell has his appropriate theorem for this particular estimator that you can look up, but so oftentimes you don't have the time to actually write down the asymptotic theory for the estimator that you're working on, and you want to get some quick and dirty estimates for your estimator for how that is distributed. And so that's where we use bootstrapping. This is a method for estimating the distribution of an estimator, or actually any statistic that's based on that estimator. It could be like a test statistic. It could be it could be like our average partial effects in the discrete choice models, or in any other model. It could be just a number that's derived from the sample in some sense, okay, or from for example from an estimator in from another estimator. So these are stochastic variables, like beta hat is a stochastic variable. So we need to know what its distribution is in order to make inference about it. Okay. And so how do you do that? Well, you kind of do Monte Carlo, not based on the data generating process, which you don't know, right? Because that's what you want to know, but based on the sample. So you resample your own data. Okay, so assuming that basically your data set is the data generating process. So it's very similar to Monte Carlo, but by treating the observed data, the sample, as if it was the population, okay, as if it was the data generating process. And so that's very intuitive in some sense. I'm going to show you the implementation in the code in just a second, but in principle, this is actually very simple. And this is another example where you can really power up your computer to do the hard thinking work for you. Okay, so here bootstrapping is an easy way to obtain standard errors, confidence intervals, critical values for test statistics. It could also be distribute. These standard errors and confidence intervals doesn't have to be for a parameter estimate. It could be for an average partial effect, or an elasticity, or something where you really don't know right out of the box what is the standard deviation, and maybe using the delta method. Well, that also requires some work. You can do that too in many cases. Other cases you can't even do that, right? So here's this is an easy way to obtain that, letting the computer do the work. And then when and why this works is much more difficult, and way outside the curriculum of a second-year course in econometrics. So don't worry about that. You will get there if you want to be an econometrician, but here's a few words about why you want to do it, and why you don't want to do it sometimes. Well, first, sometimes it's just very difficult to obtain that statistics, like I just said. And so what we haven't talked about two-step estimators, but that's what we're going to talk about next time when we talk about the sample selection model. Well, that is actually a two-step estimator, where you first estimate some equation, then you put in the parameters and predictions from this model to another equation. Well, then you can't use your standard statistics for standard errors, because it doesn't take into account the sampling variation in the first step. Okay, so but here you can use Bootstrap. And then you got basic your CLAD estimators, average partial effects, just a bunch of other statistics, but sometimes it can be difficult to derive what the asymptotic distribution is. And then asymptotics may actually be inaccurate in finite samples, as you don't know what it's converging at root n to at a rate root n to the asymptotic normal. But when do we get there? Okay, sometimes it's very fast, sometimes it's not, and sometimes you have a very small sample. So sometimes you want to derive what is a small sample properties of an estimator. And that is extremely difficult, okay? Because then you cannot rely on, central limit theorems and all the stuff that just automatically give you differentiability. But then you start to get into like some really hairy math, at least um, much more hairy than doing the bootstrap. Bootstrapping is actually often approximating the distribution of an estimator or test statistic pretty well, and in finite samples, often even more accurately. Okay, so then this sounds all good. So why don't you want to do this always? The first thing is it's computational expensive. Sometimes it's not feasible at all, right? So suppose your model it takes like it takes a week to estimate the model, or maybe 2 weeks to estimate a model on a huge computer. Well, doing 500 estimations of that model may not actually be something that is really appealing to you. Okay, so sometimes model has to be estimated, re-estimated like a 500 times to actually get a really accurate distribution. Some people sometimes you may want to do with a little bit less because that's what your computer can afford to do with the computer. Okay? Bootstrap numerical performance may be poor when estimators asymptotic variances are nearly singular. So for example, if you have, in the context of the Rolano and Bond estimator we looked at, if you have lots of of instruments and those instruments are weak, well, then you can have problems that your instruments are weak as you get a lot further and further out, and then these matrices that govern the asymptotic variance is going to be nearly singular. Okay, and so in that case, bootstrapping is not really giving you a lot of other things but noise. Bootstrap sometimes biased and shouldn't be used blindly or uncritically, but sometimes but oftentimes it's a very good approximation. Also for panel data, of course, you want to use just not the same type of bootstrap as you want to use for cross-sectional methods. Okay, so just briefly, the idea is you essentially use the data set as your data generating process. You draw from replacement from that data set, and then you estimate for each of these bootstrap samples your parameter, and then you got a parameter estimate, so you get a distribution of that. Okay, now that sounds like it's impossible. Okay, it's like you're trying to uncover what is the distribution of the population distribution of the sample without actually knowing of the population distribution of the estimator based on a sample. Okay, it sounds like something that is not feasible, and this is also why we call it the bootstrap, right? Because it's like it's like pulling yourself up by the bootstrap. So here's a little story from history. So Baron von Münchhausen, he's like both a historical character and literary character. The history goes that he lived in Germany in the 18th century, where when he was young, he joined the Russian army, where he became a captain. He retired at age 30 and lived the rest of his life as a man. So he's like really a stand-up guy. But he was known to have told very witty and exaggerated stories about he really performed in war in the Russian army. And one of these stories about was that he fell into a swamp and he couldn't get up. But then, according to the story, he would have pulled himself up by the bootstrap. Okay, sounds like completely infeasible, right? And this is why we call it the bootstrap, because it's doing something that sounds impossible, right? How can you get the population how can you get the distribution of an estimator based on on the one specific sample that you have in mind? But it turns out in the case of the bootstrap, it's working. And by the way, there seems to be a little bit of disagreement with respect to Baron von Münchhausen whether he pulled himself off by the bootstrap or by the hair. Okay, and neither thing seems to be very easiest way to get out of the swamp. But we're gonna get out of the swamp. Um, I'm I'm just saying this to say there's many different types of bootstrap, and I'm going to focus on something called the non-parametric bootstrap. That you also There's also other types of bootstrap like parametric bootstrap or a residual bootstrap. I don't know why it says bun parametric, but residual bootstrap. Um, and then there's a bootstrap for panel data. So I'm going to focus on this one, essentially where you just draw from the sample and estimate the model. Okay, here you would impose some of the parametric restrictions from the model, so you would use the model structure more to generate your bootstrap samples. So we could do that here, right? Because we have a parametric model for how y is generated depending on x and some residuals. Anyway, so here's and then there's especially in time series like so many different types of bootstrap. So I'm just going to do the overall non-parametric sample bread and butter bootstrap here. That is the following. Okay, so you estimate the model on original sample, and then you obtain some statistics. Now these statistics, these could be, for example, a parameter estimate, a average partial effect, or it could be an elasticity, whatever you want, whatever your object of interest is. And in our case, for the CLAD estimator, it's going to be the CLAD estimates. Okay. Then that you do first, okay? And then you draw a random sample with replacement from your original sample of the same size, okay? And this means that many of the observations, because your original sample is of size n, it means that many of the observations potential can appear twice. Of course, otherwise, you would not get any variation. If you draw them without replacement, well, you're just going to get the same sample again and again, and there's no variation in all your estimates. Then based on that random sample, well, you use this bootstrap sample, your sample with the replacement from your original sample to estimate that parameter again. Okay. Now I'm going to give it this index beta or b to say, okay, this is our bootstrap estimates. Are we going to do this many times, draw many samples, estimate many parameters, and then we do this capital B times. Okay, this gives us a distribution of estimates. Okay, so a distribution of statistics T, or our statistics could be the CLAD estimator. Okay, or some test statistic, for example. And then you calculate basically the standard deviation on those to get your standard errors. If you want to get standard errors on this bootstrap estimates. And that's what we're going to do. Of course, more generally, you can get the entire variance covariance matrix. If you have many aspects, you can see how these things are correlated with each other. Usually for parameter estimates, we're just looking at the standard errors. So here's a statistic. You just take the variance covariance matrix. And this, if this is a scalar value, well, then it's just going to be the variance, okay? And so you can do various different types of statistics. Nobody says that to be the variance covariance matrix. It could be the confidence intervals, okay? And then you would say, okay, you can find that, for example, by looking at the 0.25 and 0.975 percentiles in the distribution of those statistics, okay? Or you can use it to get like basically the p-values. What would that be? The fraction of time the Boots test statistics are exceeding some test statistic from the sample. Okay, so you can do many things with these distributions, and you can say essentially once you know the distribution of that estimator, well, you can, or that statistic of interest, well, you can report many different things from it, right? You can also say what is the mean of those statistics, for example. That's just a little note here on the block bootstrap. The block bootstrap, that is what you would use for panel data. And so we're not really doing that here, but we are just working with simulated some cross-sectional data. But obviously, if you do that, if you sample without thinking about the time series belonging together for different individuals, Then you're going to completely chop up the panel when you do the bootstrap. It's just draw randomly from the overall sets of observations. So what you do is you sample individuals, you sample the cross-sectional units. And so actually the principle completely the same as before. It's just that you sample you just sample sequences of observations for each individual. So here the block bootstrap would do the following. You start estimating your panel data model based on the original sample. Then you draw with replacement an individual. And that includes all the time series observations for that particular individual, so the entire sequence. And then you draw until you have a sample size of size nt, the are equal to the original sample size. So that's really just replacing what we had before. Then you do the same. You use this to bootstrap sample to do your panel data estimator, or to obtain whatever statistic you're interested in, for example, the parameters or the average partial effect or elasticities or whatnot. Then you repeat these steps 2 and 3, b times, do the same thing, you get your distributions, and you can calculate the same statistics once again. Okay, so that's a thing to keep eye on when you're doing bootstrap for panel data estimators. Well, you have to use the block bootstrap, following this recipe. Okay, so I just want to show here a little bit of Python illustration of the bootstrap versus Monte Carlo, because there are kind of subtle differences here. The Monte Carlo, well, the thing here is, here you sample from basically from the data, the population distribution of the data generating process. Okay, here you need to know how was those data generated. You need to know what the true parameters was, the distribution of the explanatory variables, and so on. And so that's well, you could rely on the observables there, but you need to know the model, the specification of the model, and so that you can simulate data from the model. Okay, it may be that you condition on some explanatory variables, whatever, but you simulate from the data generating process. You're not simulating from the sample. That's really just the main difference here between the bootstrap and the Monte Carlo. Okay, in the Monte Carlo, you sample from the data generating process, whereas in the bootstrap, you sample from the sample. It's like why it's called the bootstrap, right? You try to pull yourself up by the bootstrap by doing something that's seemingly impossible. And so here's really the difference here. That's what's going on here. I'm using this. This is a data frame, so it's like it's a inside pandas. There's a way of sampling with replacement, and that's how you do it. So it's essentially just draw the observations with your sample size n with replacement from the original data frame, and then I just use that to estimate again, and then I save the result. Okay, I do that b times. Okay, and then I calculate some statistics. So here I record what was parameter estimate, but I could also see, okay, what is the average value of all the estimates? What is my bootstrap standard error? Well, that's the standard deviation of that distribution, right? Then there's I also record the number of times where you got where it didn't converge. That can be useful information. So you're not like basing your bootstrap distribution on completely crazy non-converged values. And then the same thing with the Monte Carlo, where the only difference here is that for Monte Carlo, you sample from the data generating process. Okay, so that's the input here. Here would be data generating process, and that would be like our sim data, for example. That would be what generates the data, or here it would be a data frame with the data. Okay, so that's basically the difference. So why don't we try it out and do a little bit of bootstrapping? So here's what I want to bootstrap. So here, these functions here takes an input, some estimator, okay? And so this estimator is going to return something that's, we want to derive the distribution of. And so I want to look at the estimator for the topet. And so it's just returning the estimates there. You could return more if you wanted, and then you would get an analysis of more things, okay? Then there is a CLAD estimator is essentially returning the parameter estimates from the CLAD estimator obtained with this iterative linear programming algorithm. Okay, so this is what we do. Let's look at some results. And so here, yeah, here's the data generating process. Here's the here's our basically a simulated sample, which is just a draw from this data generating process, and then you can from the same one, and then we first present some results from the Topit model. They're printed out here, and then afterwards we get like first some Bootstrap and Monte Carlo analysis of the Topit model, and then for the CLAD estimator afterwards. And so let's just take this slowly. Okay, so this model here was generated. The data was generated based on 5,000 observations on a parameter beta equals 0 and 1. That implies we have a censoring around 23%. Sigma was equal to 1, and then there was some heteroscedasticity here. So delta was equal to 3. Okay, we have standard normal errors, and then we would expect that this Topit estimator is doing a poor job. Okay, we can actually, just as a test, just run it again. Oh man, so what is it not finding? It's because I didn't execute this here, I guess. That's also always a danger. Let's see, I didn't get this one right, maybe. Yeah, okay, so now it's running. So you can see it takes a little bit of time to do like these 100 Bootstrap samples. And, probably I should do more. So while it's working, we can talk about these estimates here. So we can verify that Topit is doing a good job. Okay, so it's doing a good job in the standard case, no heteroscedasticity. And let's see at the Bootstrap estimates of the standard errors. Well, here you got 0.3. Does that add up with what we had on this coefficient? Well, it's actually fairly close. Okay, so these parameters here, the standard errors, these are the ones that are derived from asymptotic theory and calculated as estimated parameters. And you got 0.03. So we know. And then we compare that with the Bootstrap estimate. Well, that is pretty close. You look at the next parameter, 0.5. Well, 0.51. It's actually doing a pretty good job. So that's really reassuring. You look at the last one. Well, it's same story again. Well, a little bit of precision. 0.0112, right, at 113. But what can you do, right? Maybe it gets better in larger samples. Maybe I need more Bootstrap samples. Maybe I need more a larger N for my asymptotic results to hold. Okay, so that's really reassuring. And so we are still in a world here. There's everything seems to be converged, and then we compare to the Monte Carlo distribution. They're also ballpark close to each other. Okay, so this is sampling from the real distribution. Okay. And of course, you get these, in order to judge differences between these things here, at this order, you need more Monte Carlo or more Bootstrap samples to really say if they're different. I promise you, if you increase them, they're going to be closer to each other. Okay, this Bootstrap is working in this case. You look for the CLAD estimator. Let's see here if we can see the results. I was just moving forth and back, so move it up. And then see, okay, well, what is the Bootstrap it's looking at like? It's similar to what we found for the Topit model, okay? But it's bigger, okay? It's bigger in both cases, just slightly bigger. And that, I guess, is because, we're imposing more structure with the other estimators. We get a more efficient estimator. And again, this is with the disclaimer that I only took like 100 Bootstrap samples. Now let's compare basically the estimator with a case where with Topit, where we know it's breaking down, like lots of heterogeneity or heteroscedasticity measured by this parameter delta. That is the parameter is controlling how much heteroscedasticity is. So we have a little bit more now. And then you see here, basically, Topit is not really performing that well. That should be 1, right? That parameter should be 1. This should be 0. It's significantly different from 0. But how is CLAD doing? Well, you don't want to look so much at this. We know this is all crap, right? Because we didn't satisfy the assumptions. But let's for the Topit. Then let's look at the CLAD estimator. Is it nailing it? well, here's the average across all these bootstrap samples. It's 1.00. That's pretty good. That's pretty close to one. And say you do a Monte Carlo, so here you got the average of the thetas of the Monte Carlos. Well, it looks like it's unbiased, right? It's really nailing it. And so you look at the standard errors. Well, we hope we can trust them, but but I think, looking at our example from before, where we actually knew what those standard errors were in the Topit case, were from our asymptotic statistics. I think we can extrapolate and trust these standard errors, and now we have standard errors. Okay, so even though, and that's the point, right? We got standard errors even though we couldn't differentiate the objective function with respect to the with respect to the parameters to use the asymptotic result. We now found another way, and a very powerful way that's very feasible. Okay, and so of course, why don't we why wouldn't we try to do 500 instead, right? And then look at the distribution of those parameters. It's gonna, my computer's gonna sweat a little bit. 500 times, and actually we're doing both Monte Carlo and bootstrapping for two estimators, so we have it had to chew a little bit on the numbers before we can get going, right? But that's pretty much the idea. Yeah, so you essentially use the simulation method to estimate the parameters. So yeah, it's it worth waiting for? Well, maybe I'll just pause. Yeah. So now we got our results. I had to, the computer had to sweat a little bit, and I was actually running out of power because I was running in battery, so I had to go, get the charger. Anyway, so it didn't take that long time, but we see now we have like our parameter estimates again, like before. The CLAD estimator is really nailing it. Both when we're looking at the Monte Carlo, but also when you look at the parameter estimates, are pretty close, and the average across the bootstrap samples is also very close. You got not a lot of variation, but see the standard, the true value is within the confidence interval using these standard errors. And so what I wanted to do is really just to illustrate that what you get if you basically if you plot the distributions. Okay, so I mean, just to show you, you got a number for each boot. You've got like 500 different estimates. You can plot the distribution of those 500 estimates. And here I've done it for the slope parameter, for the Topit, and then for the CLAD estimator. Okay, and so this is supposed to be one, right? And here I think the first one, that's the blue one, is Monte Carlo. The other one is the bootstrap distribution. I would say, I mean, you have to remember to look at the scale here. This is very, the variance here is not that big, and this is far away. The true value is not even on the map for the Topit. It's right out here, so it's really pushed away from the original distribution, right? And whereas the CLAD estimator, both the Monte Carlo distribution and the distribution that you get from the bootstrap sample it's fairly close, centered around the true value. So the Monte Carlo would say, okay, this is, if I get the right data, then it's fairly close to the true value. Then of course you get a data set that's a finite sample, and it's a random draw from the population. So we will get our bootstrap or our estimator, CLAD estimator. Here in our case, it was, I think it was 1.3, right, or 1.04, 1.04. So a little bit to the right of that center, and that's also what you see here. That is reflected by the bootstrap distribution. So of course, this is why you're trying to receive. I mean, here what you see is really what is the variation of all those estimates given my sample. What would it be if I resample from my data? Of course, it's going to be centered around the estimate if I use the original sample. So that's an estimate. That estimate is somewhere around here, right? So I think this kind of shows how you can generate both Monte Carlo samples and use simulations on your computer to generate bootstrap samples, so that you can get variance covariance matrices and the distributional properties of the object of interest. In this case, the parameter in the CLAD model, but it could be many other things. So yeah, I'm just going to conclude here this series of lectures on central regression models. That the Tobit model is really offering a very a very nice, well-behaved estimator that is the appropriate specification under the strict assumptions of normality and homoscedasticity, and that those assumptions are actually that's what you want to do if you have censored data and you think those observations or those assumptions of normality and homoscedasticity are holding. These two assumptions, together with the fact that you assume this is the case for u conditional on x, is implying complete independence between the explanatory variables and so on. You can then argue that these are actually pretty strong assumptions that we've seen just in small changes to the underlying data generating process can actually really give biased result for Tobit. Okay, and then it relies on these strong distributional assumptions to obtain consistency for the Tobit estimator, or consistency for the maximum likelihood estimator that we use to estimate Tobit. Fortunately, these assumptions are testable. We talked a little bit about the conditional moment test. I mentioned that you could do a Lagrange multiplier test or like your ratio test against more general alternatives, but we didn't really carry it out. I just showed this conditional moment test. We talked about that these are actually testable assumptions, and you can derive a test statistics also for the Tobit model under the null that the Tobit model is a true one, and then test those assumptions. And then we talked about various parametric approaches that relax the assumptions or for distributional assumptions. That is possible. We looked at one of them, the Powell CLAD estimator. It is always breaks down if you have more than half of the samples censored, but that's not always the case. And even in that case, you would really have to rely on a lot of hard assumptions to make the Tobit work, right? Because then suddenly it becomes very sensitive to normality and non-normality, or non-normality and heteroscedasticity. Basically, CLAD can at best identify the conditional mean of y star given x, that is x beta. If you estimate beta, you got what you want, but you can never hope to get the conditional mean of y given x in a censored sample, because then you need to impose restrictions about what the underlying distribution of the disturbances or the error term is. So the objective function is for CLAD, that is non-differentiable, but smooth out the limit in the limit as n go to infinity. It's possible to smooth it out even more, so that by adding a little bit of logit smoothing, it increases the it makes the model more well behaved and easier to minimize the objective function. Although it may actually introduce a little bit bias, so be careful how much smoothing that you add. Otherwise, you could do the censored least censored. No, what is it called? The ILPA, the linear programming. So it's not ILPA, it's LP. Whatever. P. Oh, it is ILPA. ILPA, the iterative linear programming algorithm by Bushinsky. We did that too, and but then you don't really get the standard errors if you're doing the CLAD just out of the box, out of the asymptotic box of theorems 12.3. So you would have to do Bootstrap. So we talked about how to do that. And it turns out the Bootstrap is actually doing pretty well in capturing the standard errors in our test case of the Tobit model, where we know what they're supposed to be in the limit. And also they were adding up pretty nicely with the Monte Carlo standard deviations that we could also get, because we know how these data was generated. So that's kind of all we had to talk about for sensor regression models. And next topic is sample selection.